Okay, welcome everyone to my continuation of what is algebraic graph theory, or how it looks like as it is right now, what is matroid theory. Don't worry, I'm almost done with matroids, and actually I'm almost done with the series. But anyway, I would like to talk about something really cute that kind of comes up very often in graph theory and its ramifications, and it's kind of related to the question we were studying last time, namely about the representability of matroids. So in what sense are matroids representable? Well, we already know the answer, but in what sense, or how can we prove whether something is representable or not? So how to rule out matrices. So, as a reminder, representable just means it's kind of equivalent to a matroid coming from matrices. So from columns of a matrix, and then the kind of the linear independent sets are the linear independent columns of that matrix. And how can you rule that out? You can kind of play around with the field or something like that, and there are a lot of matrices, and this looks a little bit different. Okay, so here's my reminder, and kind of the minimal example I had is this famous Weymouth matroid, I guess that's what it was called. So this was really bad. If you did not try, it was supposed to be a circle, and then it kind of made a little twink. I have no idea what's going on. Anyway, so the linear matroids, or the representable matroids, they are just obtained by this matrices by taking linear independent column vectors. So these are the linear independent sets. And some returns are not linear, so this is one not representable. So this guy here is a small example, but it's already for this guy, it's not so easy to see actually. So kind of the question would be, how can we do that? So this Weymouth matroid is not linear, and essentially the idea I try to sell you is the way to prove it would be to write down systems of equations, to assume it is, write down systems of equations, and see that there is no solution to that system of equations, which is usually not a really fantastic way of doing it. Now, in particular, if your matroid gets really large, you have many systems of linear equations. So yeah, so how to make sure that you can't solve them, you kind of need to have some better strategy eventually. And I call this recognition problems. So I kind of want to see whether a matroid is linear or not. Okay. And the idea that is borrowed from graph theory, how to do it, which is not that surprising because matroid theory is generalizing graph theory, but it's actually a cute idea. And you see it in graph theory kind of very, very often. So there is, for planarity, for example, there's a certain set of forbidden things, and it's actually really tiny. So there are only the complete graphs K5 and K3, and whenever you see those forbidden things, it's not planar. And whenever you don't see those forbidden things, I have enough quotation marks. I stopped making quotation marks. Anyway, if you don't see them, it is planar. So it's really an if and only if. There's a certain kind of witness set that you can kind of check the property on. And if you're lucky, the witness set is not too large. So in this case, it has just two elements. And there are two ways to do this, either via minus or via subdivisions. Okay. And the one I would like to address today is the minor version. So a minor is really, if you have a graph, so it's the wrong way around. So we go from this graph to this graph. So this is the minor. So this is the minor, this one. And the minor is just obtained by deleting edges or contracting edges. So here, this and vertices. So this one is contracted to contract those two, and now it's just this vertex. So really just take the graph and stack it to them. Okay, that's a minor. And it turns out for planarity, the set of forbidden minors is pretty tiny. It's just K5 and K3. And you can check that effectively. So the fastest algorithm, I think, that I know to check planarity will not quite check for those, but do something similar. And it runs in O of n, which is kind of really fast. So in n is the number of vertices. Just ridiculously fast. And you might wonder whether there's something similar for matroids, right? So is there any way for matroids to define some forbidden set of minors to check representability? That would kind of make our life much, much easier. And yes, there is. I'm just a bit annoyed, and I don't want to, well, I'm always annoyed, and life is annoying. I don't want to write down the formal definition of what a graph minor is. So let us just do kind of survey mode. So let's just do, well, the whole video is survey mode anyway. So let me just give you some idea what's going on. So you can somehow think of a matroid as being a graph configuration where, I mean, we have seen that, for example, for the Fano plane and also for, it gets higher dimensional, but anyway, and also for the Waymosh matroid, where the lines, so the highest dimensional spaces, correspond to everything that is not a basis. Always kind of confusing for the Fano matroid. Maybe you remember that the lines were exactly not the bases, and everything that is not on a line was the basis. So that's how you could think of as being a matroid. So here, for example, in our linear example, those three vectors are on a line, and as you can see, they're clearly not linear, independent, so they don't form a basis. And similarly for all the lines in this picture. And in that way, you can essentially associate a graph to a matrix. Let's forget details. Let's just say you can, and then you just use the usual minor type operations for graphs, and then you get minors of matrices obtained, minors of matroids obtained by deletion and contraction operations. That's essentially what it is. Okay. And then you can ask the same question, is there an abstraction set? And it turns out it's really tiny, actually. So here's our Fano matroid again. Fano, again, the bases of this matroid are the ones that are not on lines. Similarly for the other one. Anyway, so the representability questions can be checked by those, and that's exactly the theorem, for some fields, in particular for finite fields or over arbitrary fields. So for finite fields, there is actually a way to do it, but I won't write down the list, it's annoying. But for F2, for example, so whether your matroid is representable over F2, you only have one abstraction, which is the uniform matroid 2,4, whatever that is, just what it is. And then there's an easy graph associated. If you want to check whether something is not representable over any field, so not fixing a field and asking for that field, but something that is representable over nothing, then you need to check two things or three things, so the Fano matroid and the dual Fano matroid, whatever that is, and again, our little friend 2,4. So essentially the Fano and the dual Fano will kind of play the role doing something for F2, and U2, they can be represented over F2, so you need to rule out something over F2, and then you just put in the U2,4. And over any finite field, there's a finite list. This is super difficult to prove, and I'm also not sure how the list actually looks like. They're usually type of very complicated, but it's a nice statement somewhat. So you can check representability over a given finite field, for example, but just a finite list of abstractions. And you can do it over arbitrary fields as well, where I should really say this. I'm not saying pick your favorite field, ask whether it's representable over that field. I mean, over arbitrary fields, I mean, it's representable for everything, okay? Not many matroids will be representable over everything. And it turns out that this is essentially as good as it gets for representability. It's kind of a really nice result. You just need to check some abstraction set. But this is exactly how good it gets, because, well, finite fields are somehow, let's say, done. The list is a bit complicated, but let's say they are done. So what about the infinite ones? Well, the infinite ones are like super tricky, and there is simply no nice forbidden characterization. That's just what it is. And there's this fun example, it's called the Pels configuration. And it's just a matroid on 9 points and 9 lines. And somehow every realization needs kind of rational numbers. So you can somewhat say that this is not, or see, you can say that, not just somewhat. You can see that it's not representable over Q, because everything you do needs an irrational point. But over R, there's no problem. There's this very difficult distinction between infinite fields usually, and I haven't seen any, and I think you could somewhat argue that there's no nice forbidden factorization possible in general, which is a bit sad. So you can do something for finite fields, but for infinite fields, it kind of gets really tricky. So most of those questions are still wildly open. But anyway, after this video, anyway, we are now in a much better shape in the sense that, at least for finite fields, it's not so difficult to prove. And if you put that in a machine, it's really not that difficult, because those forbidden minor type of configurations, whatever, it's a finite list, that's usually quite efficiently checkable with a machine. So for the planar ones, it was, for example, O of n, which is like really, really, really fast. N is the number of vertices, and here, some kind of in general, it should be roughly O of n cubed, where n is again the number of vertices, which I think is a kind of a nice answer. Just ignore the infinite fields where the answer is not that nice anymore. Anyway, I hope you enjoyed this video, and I also hope to see you next time.